Hello, everyone, and welcome. My name is Michael Vincent with Keyence. We're going to give it about one more minute for anybody else that is still joining. So we'll start just about 3:04. Okay, it is 3:04. We're going to go ahead and get started. Again, my name is Michael Vincent. If you're here, just raise your hand if you can figure out how to do that within the attendee list, just to make sure that you can hear me. And I think we will, okay, there's hand going up, so we are good to go. Thank you for joining our webinar today. I'm with, it's on behalf of the tech team at the National Tooling and Machining Association. Looking forward to presenting some new technology breakthroughs that we've seen here in the last 10 plus years or so. And this webinar again is brought to you by the NTMA technology team. As we go, if you have questions, feel free to put them into the questions box, and we will get to those at either as they pop up or at the end, depending on the when I can fit it in. But we'll go ahead and get started. So first of all, here's what we're going to discuss today. A brief introduction to myself. I'm going to encourage you all to document what you see in case you have other questions. I'll give a little bit of boundaries or frame this discussion. Then we'll go through really some of what's changed in the last 10 plus years from a technology standpoint. The way that we're going to introduce some of the new technologies is by inspection scenario, where you would have them within a manufacturing shop within a plant. And then we'll get into what some of those new technologies are, and then really just a brief look or really some guesses as to what's next coming in the next 10 years. So who am I? My name is Michael Vincent. I'm with a manufacturer called Keyence Corporation. I've been with Keyence Corporation since about 2007, started as a technical sales engineer, and have been within that time with Keyence's microscope group, worked with our laser scanning confocal microscopes, done some of our 3D profilometry, and then for the last 6+ years on our CMM business, our coordinate measuring machine business. I do have my background, just so you know some of my qualifications or lack thereof. I have a bachelor in business management from the Georgia Tech here in Atlanta, Georgia. So we're going to be approaching this from a practical standpoint based on research and experience within industry. This will be less of a deep dive technical. I don't have a PhD or any kind of advanced degree that we would expect to be revealed the inner workings on some of these, but more hopefully it's a introduction to what has made its way into industry, both from the company that I work for and a lot of the other equipment manufacturers and suppliers out there in the market. So please feel free to take screenshots as you go, right? So if you haven't done this before, or if you've got a print screen button on there, if there's something in particular you want to grab, there's a great tool already built in if you're running Windows called either the snipping tool or snip and sketch. You can search for it just on your desktop there in the bottom left by just typing in snip, and you'll have be able to pretty quickly and easily find it. It's quick click and drag, and you can shoot me an email with questions on this, or just have it for your own research for later. So again, feel free to screenshot anything you see or throw questions into the question box as we go. The webinar is being recorded for viewing later, so if you miss something, you'll be able to go back and review it, or if you're not here today, and this will be here for posterity's sake. So in industry, in manufacturing, you have a few different categories or breakdowns of manufacturing, right? One would be your typical flow shop, where a part flows through from beginning to end and is worked on as it goes. The other is where expertise is grouped and by job, right? So a job shop is primarily what we're going to be focusing on today. Again, it's a production system where material flow is going to come to the machines. The parts go wherever the machines are for the next step, versus being arranged to flow from one end of the plant to the other. So not talking about factory automation, we're not talking about assembly lines really. As I understand it, most of the folks in TMA are working more in job shop, where some of the advances in technology have been focused more around programming, inspection, data integration from either one process to the next or from the front to the back, versus your larger OEMs that a lot of the technology over the last 10 years has been around factory automation. So we're going to frame our discussion. We're going to limit our focus today to job shops primarily, not including additive manufacturing, because that's had its own progression of technology and things that haven't quite integrated into, say, traditional machine shops or fab shops. So we'll keep it limited there. So Q stock technology, robot photo here. So what have been some of the biggest changes that we've seen in the last 10 plus years? Of course, software has grown in leaps and bounds and continues to grow in leaps and bounds, both from a user interface, machine learning or artificial intelligence, the emphasis and automation of reporting in whatever's being we'll say whatever's being inspected. A lot of our talk today will be about inspection. The idea of having digital twins or having a digital version of a part that exists, as well as a physical version. Camera technology has continued to improve. If you bought an iPhone in the last anytime over the last 10 years, it's improved primarily in the camera from the generation before, and it'll last about a year and a half before the next gen comes out and the camera somehow is significantly better. So there have been technology improvements in actually CMOS technology itself and the processing of those picture files and the filtering and things that can happen to those. Optics and lens technology continues to improve. And then every day, just the integration of technologies available. People are getting more creative and figuring out new and better ways of putting some of these technologies on the market together to make them more useful. As well as it affects our talk today, improvements in lighting, right? If you signed up for this, it's going to be about vision or has some vision component to it, and lighting is always a key factor in vision inspection, one way or the other. So in terms of how we're going to discuss some of these technologies, so we'll break it down into really three different situations. One would be in machine measurement, right? The other would be shop floor or in situ measurement, measuring not in the machine, but next to it, near it. And then the third one would be lab or off machine measurement, taking the parts that are being worked to somewhere else, removing it from the situation to do those measurements. And honestly, most of our discussion will be focused on these first two in machine and shop floor measurement. Happy to talk at length about QC labs and different technologies that have been released there, but most of our discussion will be on these first two, but we have a few things that actually have both shop floor applications and or lab applications, and we see them in both environments or both situations. So when it comes to measuring in machine, this is your typical view, right? This is what your traditional in machine measurement looks like. Probe on a machine coming down and touching off on a part, whether it's something simple or they've gotten to the point where they're able to do really complex shapes and complex geometries and be programmed in, right? So all this still exists. Improvements are being made to these technologies on a regular basis. With regards to vision and integrating some of the vision technology and improvements into in-machine measurement, right? So machine vision, as you typically see it, or as it's known in industry, where you have cameras watching or monitoring a process, looking for changes or looking for specific things. In job shops, they really have somewhat limited applications. I say that, but then I'm going to show a few times where we actually do have some advances in machine vision technology. But a lot of the machine vision in process work is still primarily focused around high volume production, right? Monitoring assembly line, monitoring a process. And part of it's through the environment, right? You don't want to put a camera inside of a mill with coolant and everything flying everywhere. It, splash and block the screen, need line of sight. To just the nature of job shops, you have constant changeover, and machine vision systems are great, but require programming, right? So if you're changing parts all the time, it's kind of the opposite end of the spectrum from somewhere where a machine vision system, or really a lot of the automated solutions on the market, would really shine. There have been, there's always applications for cameras for monitoring in the machine, mainly just for viewing. You maybe can put a crosshair and do some manual type measurements, or looking for specific things. But a lot of the technology that's been advanced in machine vision has been to help factory automation. That being said, if you have certain applications or certain situations, there's definitely tools on the market available for checking in process, for checking in machine, right? So this that you see in front of you, it's basically a pair of cameras that, a camera and a light source that are monitoring a part, monitoring a piece that's being worked on, or tooling for looking for certain things, whether it's measurements in particular, or whether it's abnormalities, looking for things that aren't supposed to be there, or making sure things are the way they're supposed to be. Some of this would require maybe pushing that camera system in front of the path when you go to measure. So maybe not measuring continuously while it's running, but still being able to measure without taking it out of the machine. And both these are true vision systems. This is a TMX system by Keyence, and it involves just some unique lens technology, some unique lighting technologies there. You'll see some of this in more detail on some of the shop floor measurement tools we get into. But a lot of this wasn't possible a decade ago, or some of the advances in telecentric lenses and the software to be able to process on the fly has come a long way, particularly to be able to get to a precision level that's useful for machining, that's useful for being able to inspect and validate a part that has tight tolerances. Now, the software that comes along with that too is an area that has really come a long ways in the last decade, right? So edge extraction, being able to monitor a process that when it's maybe not really clear, or to keep somebody from manually going and measuring, software is able to do that now more automatically. Machine vision software that's used in factory automation, right? The same tools can be applied for just single image measurement. So edge detection, snapping to an edge to be able to more accurately measure on the fly, removing some of the human element from it, and bring some of the automation over to the job shop world. Applying position correction, right? Checking things don't have to be lined up in the exact same way, the exact same orientation every time. Making this technology just more useful, right? When you have parts that aren't perfect, right? That aren't perfectly lined up like you might have in a high volume production setup. You can still apply some of the automation technologies available to job shops in machine measurement. Right, another one would be lasers. While not true vision, and there's still some components to it, and if we're talking things that in machine measurement, there's laser technology that's come a long way for checking certain dimensions, in particular run out, outer diameter, right, finish of a part. So this is one, and you might see a few of these that have the company I worked for have the name on it, but there are other systems like this on the market, right? So I'll be clear and try to highlight some of those, but just from a time standpoint, I'm highlighting what I had, which has some pictures that might have our company logo on there, but again, that's try to be to avoid this being a sales pitch and make it be just as educational as possible. So here in the bottom left, you see a machine tool or a part in a machine tool that if you were spinning it, you'd be able to check the run out, right? Be able to check this laser displacement sensor is really able to look for change as something is rotating, pretty much regardless of material, right? So you've got applications for this, whether it's looking through a substrate or something that's moving. And the way it's able to do this, right? It's a series of lenses with laser source, all that's being processed in a controller head. And a lot of this is new technology. We've had this type of thing's been out just for really a couple of years now, 2 or 3 years. That might have been possible or was possible in the future, but is now refined to the point or advanced to the point where it's applicable for machining, right? For the tolerances and precision needed for being useful for this industry. All right, the other thing you have there is 2D profilometers. These have advanced a good bit in the last number of years, right? Instead of just a single point, say for check and run out, maybe you need to check a profile, a series of features or steps or things as parts rotating. These can be set up one of a number of different ways. One of a number of different ways. You see it primarily in factory automation where something is passed underneath the laser profilometer and you're checking profile as it goes, but also if it's something is rotating, right, or spinning, you're able to check constant movement and check measure diameters and measure things, thanks to advances in some of these technologies, right? Lens technology getting better, lens pack and how lenses are put together and how that data is processed is come a long way. And then too, just the CMOS cameras are continuing to get better every day. This next one is an interesting release. So if this is a tool that we see for in-machine measurement that's been on the market for about a year and a half. It's an optical tracker type CMM. So if you've been around a while, you're probably familiar with portable CMMs, arm style CMMs, ferro arms, romer arms. Might be familiar with laser trackers for large scale measurement, right? Can measure 100 meters if you need to. This is kind of in between. It does what an arm style measurement system would do, but with some of the utility of a laser tracker that you can set up away from the machine. If you get into any 5-phase machining, this is very useful for checking dimensions on a part before removing it or for doing a next operation. And two, if you're measuring something while it's still checked up in the lathe, all you need is you have, or what's happening here is you have camera tracking a probe. So the user would go around with the probe and touch off on the features or touch off on the surfaces that are of interest in being measured. And the system's giving very accurate 3-dimensional data, accurate to a 1,000th of an inch. I show a large measurement envelope here, not that you typically would use it for like a 30-foot part, but this does give you the flexibility to set up away from the machine, you reach into the machine and still be able to keep line of sight to be able to measure that without really having any warm-up time. Can kind of jump right into measuring. And the reason it's featured in this presentation, it's actually a vision system. It's a breakthrough in machine vision that has real applications for machine and fab shops as well. So it's a pair of high resolution infrared cameras that are tracking these infrared LED emitters to determine the position of this probe in 3D space. So the user would, again, probe off on the features that need to be measured or they have interesting dimensions on. And just like other coordinate measuring machines, you're able to check form, you're able to check location of features, you're able to check dimensions, length, width, that kind of thing, as well as check orientation, perpendicularity, parallelism, kind of thing. I mean, look at how happy this guy is here. You can't go wrong with something like this, measuring in the machine. And it's really useful as you get into larger parts for measuring in the machine, right? But also have customers that use it for reaching into a CNC mill, of course, while it's off, and checking dimensions of a feature between operations or before, particularly if you have to take it out and put it back in a different orientation. So we call it an optical. It's called an optical tracker CMM because it's a camera, very similar to, again, laser tracker, but with kind of the utility of a CMM there. All right. Again, if there's questions on any of this as you go, just throw them into the questions box. Happy to answer them as we go, or we'll answer them at the end. So the next kind of situation I want to describe or get into a little bit, it's measuring next to the machine. Right, so if you have a part that you need to check, but don't want to take it to a lab, but can't quite measure it in the machine, right? There's been, we'll say, huge growth, right? A lot of systems released in the last 10+ years as equipment manufacturers are figuring out how to repackage their technology into a package that can be out on the shop floor, that can handle the dust, the dirt, the coolant, that can handle temperature swings. So there's a lot that's come out. I mean, one is vision-based inspection systems. Of course, I mean, you kind of knew that was coming from the title of this webinar. And there's a number of different manufacturers that have that are doing this and doing it well. So basically, all but replacing optical comparators, right? Manual optical comparators, which of course still have their place, right? But even for the same price as an optical comparator, you can get some of these low-end machine vision or vision inspection systems that, you know, are basically a machine vision system turned into quality tool, right? They have real advantages over the old optical comparators. Lighting, for one, right, is always a struggle with comparators. Being able to get light both repeatedly, if you're doing a batch of parts, right, lighting can change how the system reads what it reads, right? In vision, it's you're reading an image or reading a picture to determine what's actually there and measure off of that. So changes in how it appears will actually affect your measurement results. So manufacturers have gotten better at getting repeatable lighting, creative lighting, which I'll show some in a minute. CAD programming, being able to load in a 2D CAD file and set up your measurement requirements off of a CAD file, making these more useful for measuring out on the shop floor, partly because a lot of that programming can now be done in advance. It can be done in the office, and then you can send the program to the machine so that a machinist can take a part out, put it under the machine, measure, get a determination on the shop floor, either for 100% inspection or at least for determining and measuring criticals to avoid large batches that have to be scrapped. And these also, again, kind of comparing to your old school optical comparators, involve definitely more automation in some of the moving stages for getting to the features that need to be measured under the camera to be able to see it. And even working in some 3D. So the optics have gotten to the point, and the technology has gotten to the point where by moving the lenses up and down, and you can actually generate a three-dimensional image, or at least measure in 3D, which is of course something you would struggle to do with an old school optical comparator. Okay. Some of these, I mean, just here's some pictures of that out on the shop floor. Some things that might not have been possible a number of years ago. I mean, a lot of the systems that you see nowadays have both the optics are sealed internally, so you're not getting, you might, to maintain it, you might clean off the outer surfaces, but you're not worried about chips or dust or air getting in and getting in between the lenses and causing problems there. The temperature range is pretty wide. A lot of them are in that 50 to 95 degree temperature range. Most of them tested outside of that. It's just a guaranteed operating range, and then built to be vibration resistant. So if you have them on a cart, or the environment's not perfect, it's still able to measure. All right. Some of what's come along with that, you know, over the last number of years, precision has gotten to a point with these where it's not even close to measuring with a comparator, right? The things that you can do now, single-digit accuracy, sub-micron, single-digit micron or sub-micron accuracy, as cameras have gotten better, and a resolution of lenses and being able to read what a camera can see has gotten better. Repeatability is at a point now where it hasn't been in the past. And then size. So one of the limitations a decade ago with some of these vision systems was just the size of what could be measured, right? If you didn't have parts if you had parts that were bigger than a few inches, you were kind of stuck with some of the optical comparators or a lab-based large scale vision inspection system. So now we've gotten to the point where you've got automation built into the stages, and the ability to put some of that together with using vision rather than servos to be able to measure, you know, even up to a foot or greater on the shop floor, and have multiple views in one program. So be able to rotate the part, change it how it appears to the camera, so you can even get into some of these more three-dimensional three-dimensional parts and measuring some of those. All right. So what's driving some of these changes? Of course, improvements to CMOS technology, like I said. Excuse me, I had to mute myself to cough for a second. Higher resolution CMOS coming out every year, the ability to combine multiple cameras. The way that lenses are being made is being refined, and the way that they're being put together, right? Being able to combine to achieve the right combination of field of view and depth of field and resolution that's needed for some of these industrial applications, particularly machining applications. Right, so telecentric lenses and their applications have come a long way here in the last decade or so. And then, of course, software, like I said, is getting better every day, and the algorithms and the intelligence that comes with some of those, whether it be subpixel processing or lighting, which I'll show. I mentioned that a couple times. So subpixel processing, really, what does that mean? As the system's ability for each pixel, right, to be able to take with a finite number of pixels on a CMOS or on a CCD, right, on a receiving element, to be able to do more with it, right, to be able to extract more data from a limited number of pixels. That's able to be done one of a few different ways, but the end result is that it makes it much easier to measure fine details, to get more data points on some of your vision inspection, and then to be able to process those in a speed at which is it makes it useful, right, for a manufacturing operation. Right, there's not long latencies, there's not long delays between starting a measurement and getting a result, and it can be even on multiple features and multiple parts. And the ability to kick out bad data is just as important as being able to quickly measure good data. Right, so the tools that are there, being able to eliminate burrs or chips from an inspection just automatically, right, and be able to highlight those in the color so that if the user can see it after the result is generated to verify that, oh, yep, that is what I thought it was, or it's not what I thought it was. Right, along with that, just the way that I mentioned some of the challenges with lighting, right, with two-dimensional or really any vision-based inspection system, the way that the camera sees the part will actually affect the measurement results, right? So if it looks different from one time to the next, you'll have issues with repeatability. So what's advanced some in the last decade has been the ability to have repeatable lighting, right? Lighting that comes down to the same angle, the same is illuminating the part in the same fashion every time, and the ability to do that in different ways that will bring out features that are only brought out under certain lighting conditions. Right, so low angle incidence light, low angle of incident light to either hide certain features or to bring out contrast on surfaces. Both low angle and just coaxial illumination light, right, to be able to see everything that needs to be able to be seen, and the ability to program that. So if you have a part and you've got a batch of them, whether or you're going to be doing that part 6 months from now or a year from now, that the lighting will be consistent from one time to the next. And it's one of those advances in technologies that has been kind of flown under the radar, kind of undersold. That a lot of this vision inspection stuff wasn't really applicable a decade ago because it was cool in theory, but in practical usage, it didn't really hold up. Or from one operator to the next, you'd get different results. And a lot's happened on the market. A lot of the equipment manufacturers have spent a lot of time and effort into making sure that some of those more practical challenges have been addressed. Right, one of those being too with vision-based inspection systems, the way that a part is presented to the camera. So one of the requirements in the past for being able to measure with a vision inspection system was either fixturing, right? You had to figure out a way to present the part to the camera in a very exact manner, right? A camera needs to be placed, traditionally it would need to be placed directly in line with the part is being measured. Your part would have to be orthogonal to the camera, or else you'd get skew in your measurement. So if you had a part that looked like this, either of these, right, you have to either come up with a fixturing or you get inaccurate measurements. Well, we've gotten to the point both where fixturing has gotten easier thanks to things such as 3D printers. Can just as easily print a fixture for a part at low cost, and as you go to put on an inspection system, as well as the ability to there's rotary chucks that now are integrated into some of these machines, both the ones in the lab and the ones on the shop floor. So a lot of the struggle to get something in there just right can now be corrected through hardware and software. So you can put a part into, say in this case, it's a turn part being put into rotary chuck, which will help both for leveling and will help if you have features that are kind of on all sides of the part. The software has gotten to the point that some of these vision inspection systems out there can actually, as the part rotates, integrate what it sees into a single inspection report, into a single inspection. I've got a little video of that happening here. All right, I'll here's a turned part with certain measurement requirements, not your simplest part. The way that this system works, once you would have programmed in what you're looking for repeat parts, you'd put the part on there, push the button, you see the rotary indexing, and it's actually measuring as it indexes, whether it be those dimensions, whether it be the runout, whether it be the whole location, and all of it's gotten to the point where it's really, really quick. I think that was, I'll play it again just because I actually got another one here that shows it. Okay, so and shows you some of the reports there that come out with it. Same too if you don't have a turn part. So this is a machine part. Features on all sides, and if it needs to be inspected on all sides, now this rotary chuck will present it to the camera, move it as need be, and then give those measurements, the desired measurements. And in this case, it was a few seconds. Now, granted, all this does need to be programmed in, right? It adds a little bit of complexity to the program, but it's nothing like it would have been 10 years ago from a programming standpoint. The integration here too of AI, right, of kind of intelligent software is now when you have a part that you're presenting to some of these vision inspection systems for the first time, it can actually look at the part and then analyze it before you programmed it, right, and then suggest measurements that you would want to have on your program. Right now, oh, there's a hole here, or do you need this length? Do you need this width? And then you can go through and check boxes and basically build your program kind of from nothing with some of the advances in software that have been released. All right, so we'll move from true vision inspection systems on the shop floor. Right, it's hard to ignore the shop floor CMMs, right, and coordinate measuring machines. I showed that optical tracker CMM a minute ago for measuring in the machine, but also there have been advances in CNC CMMs. See this guy here out on the shop floor, this Zeiss Duramax is popular in the industry, both for production and for job shops. The ability to load in a CAD model and program off of that has made CNC CMMs the programming a little bit easier. It's still the biggest time consuming part of it would be programming for the first time. Right, but the environmental challenges that you typically had, the environmental restrictions that you had in the past for CMMs have been lessened. Right, some of the components are more sealed. It used to be that if you weren't in a controlled environment with the CMM, that you just could not measure. Right now, you can, with slightly reduced accuracy, still measure on the shop floor, and most of that reduction still falls within the scope of what's acceptable within the majority of machining applications nowadays. Portable CMMs, ARM-style CMMs, Faro, Romer, some of the other brands out there have had advances, in particular for laser scanning, right? Having scanners that different wavelengths of light, of laser, that will handle reflective parts better, be able to do it faster, be able to do it with improved accuracy, accuracy of 2 or 3 thou, which does open it up for more machining applications. The precision still the challenge for that. Just being able to get, you still sacrifice a good bit of accuracy compared to a CNC CMM when you're integrating both an ARM CMM and a laser, but still the improvements have made them more practical without a doubt. One new technology that was released about 6 years ago is another shop floor CMM, and I feel appropriate highlighting it here because it is optical based, just like that wide area CMM we showed a minute ago. This was it's called a handheld CMM, and it's a higher precision version of that wide area CMM, that optical tracker CMM. It has a built-in platform. Up at the top of it is a high precision infrared camera, and again, it's tracking infrared LEDs on the top of a handheld probe with a stage that can move around that has probes on it. That has infrared LED emitters on it to be able to track its position. And it's the repeatability on it is 1/10,000th of an inch or 3 microns. It's accurate to 8 microns or 3/10,000ths of an inch. So it's in that realm really of CNC CMMs that makes it applicable for machining, right? Being able to check parts right next to the machine, and being simple enough for somebody that's not a CMM programmer to still be able to use. So shop floor ready, can have it on a cart, wheel it out, either in a lab or unplug it from the big screen here on the right and show it out on the shop floor, or measure out on the shop floor. A lot of them will just live out on the shop floor. And the ability as well, so it integrates a camera with it, which is really unique. So the measurements that you're getting, it's not your conventional CMM type view. Instead, it's integrating augmented reality, right? If you've heard that, you're overlaying data on top of the picture of the part that's captured live. So it makes it much easier for an operator to understand what they're measuring. Okay. Hard to get past this without talking about 3D scanners. So while they're not really true vision technologies, there's still some receiving elements there that maybe it applies for this. But regardless, it's 3D scanners have come a long way in the last 10 years. Right, so and I'm going to talk strictly about metrology grade scanners. Of course, there's a kind of a whole market for consumer grade or hobbyist type scanners out there that really don't offer the level of precision needed for industrial applications. But for metrology grade scanners, they are improving in accuracy. The price is coming down to a point where they are being purchased by machine shops. And really where they shine is when you have contoured parts, right? Tooling, molds, impellers like you see here, things where you really need to understand that profile and can't afford to miss data that a probe may or may not hit. Right, a lot of the CNC CMMs or that handheld CMM we're looking at a minute ago has contact-based scanning on it, right, which can be useful. But if you really need to understand the form of a part and the profile and not miss any data, a scanner is going to give you all that information. And their limitations, right, some of the limitations haven't really changed, right? They still struggle with edges and holes. And so if I were using a scanner here, like in this picture on the bottom right, where it's going to be really useful is for understanding the flow or understanding your height changes across this with your stress, your contour. I probably wouldn't use it as much for verifying hole location and hole sizing on this part on the bottom right, as much as I would trust the conventional CMM. But some of this data is that you can only get with a scanner, particularly at the speed that you're talking. Right, you can collect data with a scanner in a matter of a minute, a couple minutes, and then process it. Right, and that's still the biggest bottleneck is the processing time. They do still require usually somebody to clean it up or to analyze the data to verify that what it's seeing is real, right? To see what's an artifact or what's real data. So still a little bit more of an engineer's tool, or you would have somebody that's a little bit more 3D proficient operating something like this, rather than just blindly trusting the data coming out of it. But the software is improving to the point where you're getting less and less bad data and more useful information as scanning techniques and the ability to process it improves. All right. Another kind of the next phase or the next step up in terms of precision from a 3D scanner would be, we'll call them 3D surface profilometers. That's something that wasn't on the market 10 years ago. The ability to, instead of having a contact-based profilometer that would drag across a surface, have basically a higher resolution 3D scanner, whether it be laser or white light or blue light based, that's going to analyze a part or measure the surface of a part, generate a 3D model, and then the user is able to measure off of that three-dimensional file. Great for checking profile, great for checking contour. We'll see it a lot on ceiling surfaces, things that have tighter tolerances. Things need to fit together very well, and you really need to understand a surface. Right, these 3D, this is one from Keyence, but there's others on the market, right? A 3D surface profilometer or optical profilometer lets you get that data, and the collection time too is fast. You're talking 5 seconds, maybe 30 seconds if you're going in kind of a higher resolution mode. But put the part onto there, let it scan it, and you've got a 3D surface model that's generated in a minute or less that then you can analyze. All right. The next, I guess, step up, tip of the spear, we'll say, in terms of accuracy or precision is laser scanning confocal technology. A few different manufacturers of those on the market now, but this is going to be if you're really trying to understand surface finish, right? If you're really trying to understand surface roughness, This will use a high resolution laser to scan a surface, to raster across the surface, and then generate a 3D image like you can see there in the bottom middle of your screen. It doesn't, different than an interferometer, it does not have to be perfectly flat. And it also, because it's laser based, it's material independent. So if you have really shiny, if you have a matte finish, if it's all white, right, or all black, the technology is still able to pick it up. But for our discussions here, yeah, if you've got a mirror surface that it might be difficult to measure optically, like this is these laser scanning confocal systems, microscope systems are able to check that. Some of the applications, right, if you really need to understand, say, radius measurement on a drill bit, or showing cutting tool wear analysis. Those are practical applications for it. Particularly if you're really trying to push the limits of what's possible with your tools. If you're really trying to understand where and how, and the speed at which tools are wearing, or at which understand one process and how changes affect that process. This is a good tool for quantifying that data really easily and really, really well. So just another example here, right? If you're comparing multiple surfaces, so you applied a different process to 3 different surfaces and need to understand what that looks like, volumetrically analyze from one to the next. This is a tool that would be able to do that. Rather than just visually see, you're able to put numbers and data to it, and then really process and understand how changes to a process affect the results. So yeah, we'll see these technologies in a number of different industries, but metalwork and machining's fits in with that for sure. And then again, there's also a class of tools or class of systems out there for checking tools specifically, right? So there's a few different manufacturers that will, say, optically magnify your tooling and then check that, make it easy to understand, do some of those measurements. Either, usually it's not in process, but you've got a system right next to the machine that you can understand tool wear. If not with a laser scanning, with a camera and software that's able to check that, track that, and really even feed that data back to the machine. Technology's gotten to the point now where it'll feed the results back into the machine and can adjust your tools on the fly. Zoller, one of the leaders in this, has some really interesting technology that kind of takes from start to finish. We'll take some of that data and then feed it back in and help you make adjustments and document, even barcode, generate QR codes and help and read those as well before tracking some of your tool wear. All right. Okay, so some of the lab-based tools out there, so vision inspection systems like you see in the bottom right, your traditional OMMs, optical measuring machines. CMMs have gotten to the point where now you've got multi-sensor CMMs. Instead of just probing, they might have a camera or have a laser also integrated into the head of your CMM, like you'd see in that picture in the top right, letting you measure more, let you better understand your part in greater detail. Digital microscopes or something we see, and we see these in machining applications and machine shops, whether it be for metallography, for looking at grain structure of metal, or for fracture surface analysis, or just for general understanding of processes. 3D scanners, like you see this guy in the bottom left, he's holding a handheld 3D scanner. That's something that's come a long way here in the last 10 plus years. And then the holy grail, the black box, CT scanners, computed tomography. One thing that we hear regularly when we visit customers is just this idea that if there's a black box out there that I'm sure that exists, I can just put my part inside of it and it'll measure everything inside and out and get an idea of it and just give me all the dimensions. And the closest thing to that really on the market now is computed tomography, is a CT scanner. Which they're great, still limited by size and really cost prohibitive for most shops at this point, starting at about $500,000. This, like I said in the beginning, most of the technology I was introducing is more for in-machine and shop floor. A lot of the shop floor tools used to be strictly lab-based tools that have now made their way, have evolved to the point where you can use them out on the shop floor. Of course, you can put all those in a inspection lab and a QC lab if you want as well. So in terms of what's next, like what the next 10 years hold, I mean, that's that's anybody's guess, right? But I mean, some of what is knocking on the door is some like quantum computing or quantum breakthroughs in some of the quantum photonics, and what that's going to do for circuits, and what that's going to do for ability to process. Really, every feature, that every technology I showed here could be improved by the ability to better, faster process more data. Digital signal processing is going to improve with that. Just all kinds of things, improvements as well on the software side, right, for artificial intelligence. A struggle still today for job shops is the ability to receive a print or receive a model, receive a measurement, or I'm sorry, receive a job, and then set about making that part and inspecting that part as quickly as possible. The bottleneck is still on a lot of it on the front end, the programming of the machines, the programming of the inspection systems to look for the specific call outs for checking the criticals. Somebody has to set that up. And I'd expect that to be improving in the next 10 plus years. The demand is there, the technology is there, and I'm sure people will put them together. Although right now it's still a gap in the market. There's still not an easy way to just load in a model and have your machine run automatically, and then have your CMM check it automatically, or have your 3D scanner check it automatically. Shoot, even with the 3D scanners that you've got, they can collect the data, but then somebody still has to tell it what on the data needs to be analyzed, right? What needs to be checked. So still some room there. And then processing time. I mean, with some of that improvements in computing. I mean, if you have scanners, especially large scale scanners, right? It could take you 5-10 minutes, maybe even an hour, depending on depending on the job, to collect all the scan data that you need, but then it can take you 40 hours to even compile all that data, to process all that data, depending on the amount of data collected. So how these systems are able to handle large data files, I'm sure will continue to advance as the time required for processing continues to be a bottleneck for scanners. So what else? I guess if you have questions or suggestions or things that you'd like, do you here in the audience, do you see anything that could be on the horizon that could be in the next 10 years we'll see more of, that will be having an impact on our industry? Please throw it in the questions. Really, that's kind of the end of that is the end of my presentation. I'm happy to answer questions on on any of these. I appreciate the questions we do have here, but now would be a good time if you have questions, enter it in the question box. If you can't quite figure the question box, just throw it into the chat there. But I'll give you all a second to throw some of those in there. I have a question about pricing for a lot of these. That is something that really I'm going to avoid on this webinar, on this presentation. So if there is pricing for specific products, feel free to reach out to me specifically. A lot of these, I mean, they have come down in cost. Almost everything I showed here for your shop floor measurement tools would be considered drastically cheaper than a conventional CMM, right? Coordinate measuring machines, which for a new one can start at $50,000 and go up to $1 million depending on the precision. So most of the things that are being discussed here are under the $100,000 mark for a lot of the technologies that are on the market. So cheaper than machine tool, cheaper than CMMs, but still a big step up from hand measurement tools. Again, I'll give a minute for some more questions. All right, somebody asked about take a look at this wide area CMM again. Specifically environment. So this guy, right, it's built for shop floor. What you see here, this view, this is the internal view. So the cameras here are sealed. So it's not a tool that necessarily is built for a lab, right? And in terms of your precision on here, I mean, you're basically have accuracy of 1/1000th of an inch for every 10 feet that you would measure. For most of the parts that we'd be seeing in machining, you'd expect it to be accurate right around 1/1000, versus some of the arm style CMMs, and we're talking specifically volumetric accuracy versus your arm style CMMs that for the same size, you'd be looking something more in the 2 to 3 thou, 2 to 4 thou range, average of 75 microns for like a 4 meter arm. So just then credit the high resolution camera, the optics, the integration of the technologies there that weren't possible a number of years ago. All right. Well, that's all the questions that I see. I do want to say thank you for joining today. Yeah, for those that were in attendance, I appreciate the questions, appreciate your time. If you happen to grab a screenshot, feel free to send it along with your question to me directly. And if there was no further questions, we'll go ahead and end our session here. But again, thank you all for coming. Thank you all for joining. And hope you'll have a productive and fruitful rest of your day.